So hello everyone, welcome to the channel. So in this video I'm going to show you the historical climate classification using ERA5 and MODIS Terra dataset using K-mean clustering model in Google Earth Engine. So now let's get started. So we're going to perform a climate classification using a K-mean cluster model in our Earth Engine, a machine learning approach. So this video we're going to implement a climate classification using K-mean clustering algorithm with Google Earth Engine. So it utilizes ECMWF ERA5-Land climate dataset to analyze the temperature and precipitation data over 20 years of period from 2000 to 2020 across a defined geographic region. So basically the code segments the regions into 4 climate zones by clustering the similar climate patterns and then visualize the classified map using distinct colors for each climate classes. In addition to clustering, the code calculates and plots key statistics such as the area per climate class and temperature trends. It also integrates the MODIS NDVI data to monitor the vegetation health for a specific climate classes over the time and generating a time series analysis. This approach leverages the machine learning to explore and classify the climate trends and offers insight into the spatial variation and the impact on vegetation. So let me get back to Earth Engine. So to define your study area, so we're going to navigate to this option here. So let me delete my study area here. I'm going to select this option here. So I'm going to click this option. I'm going to delete my existing study area. And now I'm going to show you how to draw a study area, how to create a study area. So I'm going to click this option called draw a rectangle. So I'm going to cover the southern part of the India here, the peninsular area. So I'm going to cover all the peninsular India. So now I have created a study area here. So now which gets reflected here in this section. So import variable geometry. You can click this option called show generated code. And now I'm going to copy my latitude and longitude of the study area. I'm going to copy it using Ctrl C and I'm going to close it. And now I'm going to paste my latitude and longitude in this code here. I'm going to use my Control key and V together and I'm going to paste it my latitude and longitude here. So I'm going to arrange it. So now I have inserted my latitude and longitude of this particular study area, that is peninsular India. And now to define the region of interest using our latitude and longitude, I defined this variable called region coords, represents coordinates. So containing latitude and longitude of this study area in the 4 corners. And now to create a geometry objects from this coordinates, we define this variable called a region geometry equals to geometry.polygon. Region coords refers to our variable containing the latitude and longitude. So now to add this layer, so we define map.addLayer and referring to this variable region geometry with the default visualization parameter and output the layer as study area. So once you did that, we can center our layer by using this set of code here. So map.center object region geometry. You can also add your zoom level here. I'm going to add a zoom level of 7. So next step, we're going to load our ECMWF ERA5 land dataset here. Now let me show you that dataset here. So this is our ERA5 land monthly aggregated climate reanalysis. So the dataset is availability is from 1950 to 2024. So a historical dataset is available in this climate dataset, and the dataset provided is the Google and the Copernicus climate data store. And using this specific code, you can able to access this set of datasets here. So now we're going to navigate down. So here you can able to visualize the resolution of this particular band is around 10,000 meters. So accurately it is around 11,132 meters. So a few description about this dataset here. So ERA5-Land is a reanalysis dataset providing a consistent view of evolution of land variables over several decades at enhanced resolution compared to ERA. So ERA5-Land has been produced by replaying the land component of ERA5 climate reanalysis. So you can go through this dataset description here. So let us view the different bands that is available in this dataset here. So in this dataset, you can able to visualize there is a variety of bands that is available. So we have a lot of different bands. You can just go through the different band that is available here. So we're going to specifically focus on this particular band, that is temperature 2M. So the temperature of air at 2 meters above the surface of land, sea or inland waters. The 2 meter temperature is calculated by interpolating between the lowest model level and the Earth's surface, taking account of an atmospheric condition. And similarly, we're going to focus on another set of precipitation band here. So we're going to move down here. We're going to search for this precipitation band. So now here you can able to see this is our total precipitation sum. So it is in meter. So accumulated liquid and frozen water, including rain, snow that falls on the Earth's surface. It is some of the large scale precipitation and the convective precipitation. So the precipitation variables do not include the fog or the precipitation that evaporates in atmosphere before it lands at the surface of the Earth. So you can go through. There is a lot of bands that is available in this particular dataset, and the link will be given in the description for this dataset. So I'm gonna get back to the Earth Engine. So to load this dataset into Earth Engine, we have defined this variable called ERA5 equals to Earth Engine.image collection ECMWF ERA5-Land monthly AGGR. So now next we're gonna filter with a specific time period. So for example, I'm gonna filter from 2000 to 2022, that is 2000 to 2020. So around 20 years of datasets. So this particular dataset is availability is from 1950 to 2024, that is present. So in that I'm going to specifically focus on from 2000 to 2020. So next we're going to select specifically two bands from this particular dataset. For example, we're going to select this band called temperature 2 meter, and next band is the total precipitation sum, that is the second band. So to define this variable called climate variables equals to ERA5 data dot select. So I'm going to select this per two bands, that is precipitation 2 meter band and the total precipitation sum band. So I've already shown you, let me show you once more time here. So this is our temperature 2 meter band, and the second band, the total precipitation sum. So I'm going to get back to Earth Engine. So next we're going to check for the number of images that is available for the specific timeline for this study area, that is peninsular India. So I'm going to mention this code as a print, and I'm going to copy and paste this variable, that is climate variables. I'm going to paste it here, and now I'm going to run this code. And now let us visualize the number of images that is available for the specific study area. So also I'm going to adjust the zoom level here. It's kind of zoom level is a bit higher, so we're going to reduce the zoom level to, we're going to reduce the zoom level to 4 here. And you can visualize in the console section of this image here. I'm going to click this arrow button here, and there is around 240 images available in this specific study area, that is peninsular India. You can able to see. So there is around 240 satellite images being available. So you can able to visualize there is around 240 images available for the specific study area. So there is a lot of satellite images available for the specific timeline. So next we're going to combine this climate variable into a single image stack. So that is, we're going to combine both this temperature and total precipitation climate variables into a single image stack. So to do that, we're going to define this variable called climate image stack equals to climate variable dot two bands function. So basically we are using this two band function in order to stack the temperature and precipitation band into a single image stack. So the stacks, basically it stacks the temperature and precipitation bands into a single image for processing, and stacking is necessary for a multivariable clustering. So now to visualize the details of this image here, that is after stacking, we're going to visualize the details of this particular image now. So I'm going to mention I'm going to copy this particular variable name here, and I'm going to paste it here. And now we're going to run this code. So now let us visualize the result here. So previously it was around 240 images was available. Now it is around 480 elements, that is bands available. So you can able to see this. We have kind of separated the temperature and precipitation bands. So previously in the image here, so it was both of them, both the bands were together in a single image here. So you can able to see it. Both the bands were together in a single image. So after stacking, we have separated the temperature and precipitation bands separately, which is indicated in this image here. You can able to see this is temperature, and this is the precipitation band, and similarly temperature, precipitation, temperature, precipitation. So to stack the climatical variables into a single image, we have separated the temperature and precipitation bands separately for each image. So that's why the previous it was around 240 and now it is around 480. So now next we're going to sample the climate data to get the training data for our clustering. So to sample the climatic data, first we need to get the training data for our clustering model here. So we are using the k-mean clustering model because in order to classify the climate data into different classes, so we are using the specific model called k-mean clustering model. So first to get the sample the climate data to get the training data for the clustering, so we need to do sampling for the training purposes. So to get the training sample, we define the variable called training sample equals to climate image stack dot sample. So it automatically samples the training sample. So next we define the region, that is our region study area, that is region geometry. So this is our region geometry here, which is indicated here, this one. And next is a scale, that is a spatial resolution of this particular dataset, that is around 10,000 meters. So num pixel here, meaning the number of sample we want to have for each unique pixel. So for example, I'm going to have 100 samples for each pixels separately. So after the samples, after the sampling, the samples are collected. So once the samples are collected, we need a model to train it based on the collected sample. So for that purpose, we are using the specific model called k-mean clustering model. So for that we defined a variable called k-mean model equals to earth engine dot clusterer dot vika k-mean, and we have mentioned the number of classes to be around 4. So you can select the classes of your up to your choice. So I've selected the number of classes to be around 4. So the k-mean cluster model is kind of an unsupervised classification. For example, when you don't know what kind of pattern or what kind of classes you have when you don't have any information about the classes in your region of interest. And also this clustering is very useful. For example, whenever you want to find a specific pattern or a similar pattern in the precipitation or in the temperature, and but also what you have a large number of data and it is impossible to find it manually. So this clustering technique will help you to understand what kind of pattern experiencing in each of the pixel. So here we have defined 4 different class or the clusters or the patterns, the 4 classes based on our historical climate dataset. So next we need to train this model based on our training sample. So for that I have defined the dot train and training sample referring to the training samples here. So here we are training our k-mean cluster model with 4 classes based on the collected samples here from here. So unlike the supervised classification in which you know the number of classes and you know about the samples for each class separately, and you have a basic knowledge about the different classes characteristics in your study area, but here we don't have enough knowledge, and also we just have a bunch of data in a single layer stack, and we want to do a classification for based on the patterns that is available in these historical climate data set, and also the samples are collected before So the only thing that matters is the number of classes you selected. This is totally optional. It is up to you. So you can reduce the samples or increase the samples. So for example, if your study area has more climate zones, so in that case you can just increase the number of samples for your region of interest. So next we're going to apply the model to classify the climate data into clusters or classes. So to do that, we define this variable called climate classification equals to climate image stack. So the climate image stack, which is referring to this particular variable here, that combines the climate variable into a single image stack, and dot cluster, we are referring to our model, that is k-mean model. So representing this particular variable, that is our k-mean clustering model, and we're going to rename as the climate clusters. So for that we define dot rename climate clusters. So next we display the classified climate map and clip to based on our study area, that is our region of interest. So to do that, we define this code map.add layer climate classification referring to this particular variable dot clip. So based on our study region, that is region geometry, and we are setting a minimum of 0 and to a maximum of 3 because we set 4 classes or the clusters. So for that, starting from 0, 1, 2 and 3 representing 4 classes. So for that we define a minimum of 0 and a maximum of 3. And the color palettes, we define the following color palettes: blue, red, orange and green, and output the layer as climate classification. So once you did that, we're going to run this code. So we're going to navigate to this option called run and going to click run. So now here in the geometry inputs, I'm going to turn this off here. So we're going to navigate to the layers section here, and I'm going to turn on the climate classification. So it's going to load that layer so you can able to visualize. So it is a peninsular India. So from this image you can able to visualize we have 4 different classes here. So this particular is black is the first color, and white is the second cluster, and the gray is the third cluster, and this particular color light gray, it is our 4th cluster. So you can see the different classes based on the precipitation and the temperature variations. So in our region of interest, that is our peninsular India. So here the different classes or the clusters here, which represents the different characteristics for the precipitation and temperature, and also we have 4 different classes. So I'm going to navigate to the layer here. I'm going to click this option. So you can also add some color to it. So I'm going to choose the color palette here. So I'm going to add some color to it. So first I'm going to select blue, and followed by I'm going to select red and orange, and last you're going to select green. So you're going to apply. So now you can able to visualize it in different colors here. So you're going to close this. So for example, so the blue region here, which represents the temperature and precipitation, which experience a similar pattern of temperature and precipitation, and similarly the red areas, which indicates the classes the different classes which experiencing same temperature and precipitation, and also the orange one here also, which represents the same class experiencing the same temperature and precipitation, and similarly the green. So next we're going to export this classified image to a Google Drive. So to export to do that, to export the classified climate map to Google Drive, we have to define this export.image to drive, and image we are representing as a climate classification, and the description is climate classification map, and the spatial resolution, so the resolution of this particular dataset is around 10,000 meters, and the region is our study area, that is our region geometry, which represents our peninsular India, and the coordinate reference system is EPSG 4326, and the folder we're gonna save this in our Google Drive is climate analysis. So next, to calculate the area in square kilometers for each climate classes. So now to calculate the area of each class in square kilometers, we define this variable called area calculation equals to earth engine dot image dot pixel area function. So the pixel area will be an image including the value of the area of each pixel separately based on the square kilometers, that is in square meters. So if you want to convert to in square kilometers, we're going to divide it. So dot divide 1 is to 10 power 6. So we're going to divide it by, so in order to convert from square meters to square kilometers. And last we define dot add bands. So next to the image we want to have the climate map, that is the map that the all regions divided based on the clustering technique. So now to visualize the details of this particular variable area calculation, we're going to define as a print here, and we're going to place this particular variable here. So in order to view the details about this variable, so I'm going to place it here, and we're going to run this code again. So we're going to navigate to this option called run, and we're going to click run. So now in the console section you can able to visualize the image has two bands here. So it has two bands. The first band which represents the area, so which showing the pixel size here, the area band which shows the pixel size. There is the first band which shows as the area, which is in float data type and coordinate reference system, and followed by the second band, the climate clusters, which is shows as the data type and the coordinate reference system and the pixel size here. So now to how to visualize the area for each climate classes. So to do that, we define this particular, we're going to create a plot. So plot a chart to show the area of each climate classes. So to do that, we define print ui.chart.image dot by class, and image we are referring to the area calculation, that is referring to this particular variable here, and the class bands refers to the climate clusters. So the climate clusters which represents this particular variable here, that is we have renamed our model climate classification variable as a climate clusters. And next is the region, that is our region geometry, which represents our study region, that is our peninsular India. And to reduce, so here the reducer is very important here. So we have the area of each pixel, and we have the border of each classes. So if we want to get the total, so to get a total of the each of the clusters of the classes, so for that the reducer must be equals to sum here to get a total area for each of those clusters or the classes. So for that we define the earth engine dot reducer dot sum function, and the spatial resolution we are set to around of 10,000 meters. And the last we have some set of an title and h-axis and v-axis. So to do that, we define dot set options title area per climate class in square kilometers, and title we define climate classes, and v-axis we define the title as area in square kilometers. So you can able to visualize from this image here. Let me reduce this. So you can able to see this plot here. This is the plot. So in this axis we are represented in area in square kilometers, and this axis are the climate classes. So you can able to visualize the total area here, which is around 1,378,944 square kilometers. And similarly, the red class here, which indicates has around 444,733 square kilometers. And similarly, the orange class and the green class. And these are the different classes which corresponds to the map here. So the blue class which represents in this particular map, and the red one which represents in this map here, you can able to see that. And similarly the orange and green which corresponds to this map here. This plot corresponds to this map here. So next we're going to calculate the mean temperature in Celsius. So next we're going to calculate the mean temperature in Celsius. So we're going to convert from Kelvin to Celsius. So to do that, we define a variable called average temperature equals to ERA5 data dot select. We're going to select from the dataset the temperature band here, temperature 2 meter, and in that we're going to mention as a mean function here to in order to obtain a mean value. And we're going to subtract with the value 273.17 value in order to convert from Kelvin to Celsius. So for that we define this. And next to create a temperature map with the we're going to create a temperature map with the classified climate data. That is, we're gonna find out each of the class, the minimum and maximum temperature for each of this climate classes here. So to do that, we defined a variable called temp with classification equals to the average temperature. So referring to this particular variable here, dot add bands. So the add band function basically allows us to add a new band next to the temperature band here, and the new band will be the climate classification, that is this particular variable. So we are referring to the climate classification band. So I'm gonna show you that. So here, so this is our climate classification variable. So there is a band we're gonna add into this particular temperature band here. So we are doing it so because we want to have an average temperature for each of this classes, for each of this classes, climate classes. So for that we're gonna add this with temperature band with climate band classification band here. So for that we define add bands climate classification. So next, to calculate the temperature statistics, that is minimum and maximum temperature for each climate classes. So next, to calculate the temperature statistics, that is minimum temperature and maximum temperature for each of this climate classes here. So for that we define a variable called temperature stats equals to temp with classification, referring to this particular variable here, and dot reducer reduce region, and the reducer we defined doubly dot, that is earth engine dot reducer dot mini and max function. So next we define doubly dot reducer dot mini max function here. So the mini max function is a reducer applied to that image. So it calculates a minimum and maximum value for each pixel. In this case, it computes the minimum and maximum temperature for each of this climate classes. And dot group 1, which represents the group 1 is a group 1 function is a modifier used to group the result by certain class of the categories. So it is hence here it is a group the calculated statistics by a climate class. Basically the number 1 represents the band index for the climate class in the image stack, which means the temperature statistics will be calculated for each distinct classes for class 0, 1, 2 and 3. And next is our geometry, which represents our study region, that is region geometry, and the spatial resolution, that is around 10,000 meters, that is the spatial resolution. And we're gonna visualize to visualize this result, we define print temperature statistics by climate classes, and referring to our variable temperature stats, so referring to this particular variable here. So you can able to view here as a temperature statistics by climate classes. So we're gonna click this arrow here. So we have the 4 groups here. So the group 0, which represents the class 1, that is the blue color. So the maximum temperature is around 28 degrees Celsius, and the minimum temperature is 22 degrees Celsius, and which is represented as group 0. So it is group 0 and has a maximum and minimum temperature. Similarly, the group 1, which has a maximum temperature of 27 degrees Celsius and the minimum of 16 degrees Celsius. You can visualize the temperature. These are the region, the green areas. So this is the second class, which is red, has a maximum of 27 degrees Celsius and minimum of 16 degrees Celsius, which are represented in these areas, and followed by the group 2, that is group 0, 1, 2, so maximum of 28 degrees Celsius and a minimum of 17 degrees Celsius. And last is a group 3, has a maximum of 26 degrees Celsius and a minimum of 21 degrees Celsius. So the group 3, it is this particular color here, which is indicated in this areas here towards the northeastern section of this peninsular India, which represents as the group 3. So you can able to see here. So we are grouped based on our climate classes with the maximum and minimum temperature. So now here we can able to observe here the group 0, which has a maximum temperature of 28 degrees Celsius and has a minimum of 22 degrees Celsius, and also in area wise the blue classes has a very high area compared to the other climate classes. So we're going to select the pixels classified as a 0 class, so which represents our blue. So to do that, we're going to define a variable called class 0 mask equals to the climate classification equals to 0. so representing the class 0. So basically we're going to select this particular climate class 0, and we're going to check for the NDVI changes over the period of time from 2002 to 2020. So to do that, we're going to use our MODIS dataset here. So let me show you that. So this is the MODIS Terra vegetation index. So this particular dataset is available from 2000 to 2024. So these are the following bands that is available. We have our NDVI band here. So we're going to use this particular band. So I'm going to get back to Earth Engine. So I'm going to define a variable called MODIS NDVI equals to image collection MODIS 061 MODIS 13A1. This is the code to access the MODIS dataset here. And the spatial resolution of this particular dataset is around 500 meters. So we're going to filter with the specific timeline from 2002 to 2020. So to do that, we define dot filter date 2020, that is 2002 to 2020. And so we're going to create a loop here. So dot map function image, we define a variable called NDVI band equals to image, referring to this MODIS NDVI, and in that we're going to select this particular band, NDVI band here. And we're going to apply scaling factor. So that is we're going to multiply with 0.0001, and we're going to return the NDVI band and update mask, the class 0 mask. So class 0 mask represents this particular class, that is class 0. So that is this particular class here. So we're going to check for the NDVI changes only for this particular class 0. There is our climate class. We're going to dot copy properties to this image, and image dot properties names. So there is our input image properties. So next we're gonna create a time series chart for our NDVI changes for the class 0. So to do that, we define ui.chart.image.series and image collection referring to MODIS NDVI. So this particular variable, and that is this particular variable MODIS NDVI, and the region, that is our region of interest, the study area. Regional geometry represents this particular study area. And reducer, we define earthengine.reducer.mean function to acquire the mean NDVI value and the spatial resolution of around 10,000 meters. And X properties, that represents the system start time, that is starting from 2002 to 2002. And we're going to set an options for this particular chart here. So to do that, we define set options. Title NDVI time series for class 0 from 2002 to 2000, and H axis we define the title as date, and V axis we define mean NDVI, and we're gonna give some color to the graph here. So for that, we're gonna specifically mention the green color, and let us visualize the result. So now here you can able to see this is a plot NDVI time series chart for the class 0. So class 0 is our this particular color, that is blue color, and in this axis which represents the NDVI mean, and this axis represents the year, that is date, from 2002 to 2020. So let us visualize it here. So this is the NDVI time series chart for class 0. So from this, so you can able to observe here the NDVI, high NDVI value which indicates very good vegetation growth, and low NDVI value which represents the non-vegetative areas such as the water bodies or the urban areas. So here in this particular timeline, that is in 2002, there is a high NDVI value of around 0.5, and comparatively there is a low NDVI value in 2003 in May 25, and we have very high value in September 14, 2002, and similarly here high NDVI value were observed in September, and low NDVI value is observed in April and as well as in May, and high NDVI value is observed in September in 2004, and similarly low NDVI value was observed in June and also here, that is in April, and very low was observed in June. So likewise you can able to see there is a high NDVI value was observed in the September, and the low NDVI values were observed in May, April and June from 2002 to 2020. It is because in peninsular India, so during the summer period, that is so in peninsular India, so from April to June, so it is a very high temperature summer period. So in this particular timeline, you can able to observe the NDVI value has been dropped significantly, and during the September September, October and November, it is a rainfall season. So during this time that we can able to observe there is a high NDVI value being observed, which is consistent throughout the year from 2002 to 2020. You can able to observe the consistency. In certain areas there is a spike, which is for example, this particular time our NDVI value was dropped very low, around 0.2 in July, and comparatively the NDVI value has gained higher during the September, and it dropped it during May. So you can observe during the summer season the NDVI value has dropped significantly, and during the rainfall season the NDVI value has been improved significantly. So I'm gonna get back to my earth engine here. So you can able to see there is a correlation between our NDVI value and the rainfall and the temperature. So during this part of the peninsular India, which is represented in blue, that is the class 0, has a very good NDVI value during September, and it has a very low NDVI value starting from April to June and sometimes in July. So this entire blue class are represented as a class 0. So there is a correlation. So during the summer has a higher NDVI value, so higher temperature, which results in lower NDVI value, and comparatively lower temperature time, that is during rainfall season, there is a higher NDVI value were observed in this set of class here, in the blue classes here. So you can able to see here this image. So you can able to observe here the blue region, which indicates the temperature which is ranging from 28 to maximum temperature of around 28 degrees Celsius to minimum of 22 degrees Celsius. So we found a significant correlation between the climate data, that is temperature, rainfall, and the NDVI value. So in this video we have shown you the historical climate classification using ERA and MODIS Terra dataset using K-mean clustering model in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like.